In this video, we will do some examples using the Fundamental Theorem of Calculus Part 2. So I want to begin with example 2 here. We have the definite integral from 1 to 9, x squared plus 1 dx. So we actually found this definite integral, this area under the graph of x squared plus 1, over this interval from 1 to 9, using Riemann sums, using a limit of Riemann sums. And we got 752 over 3 with Riemann sums. And it was doable. It just took us a while. The process was tedious. Maybe it took us 15 or 20 minutes to work that out in the previous video. So let's see how fast this is with Ftc Part 2. Ftc Part 2 says, well, we can do this by doing an antiderivative. Antiderivative of x squared is x to the third over 3. And an antiderivative of 1 is just x. And now I have to plug in 9 into this, plug 1 into this, and subtract what I get. So there's a notation to indicate that. What I do is I write a vertical line at the end of my expression. Let me put a parentheses around this to indicate I'm going to plug into both. I write a 1 at the bottom and a 9 at the top. Okay, so the notation here, let me write that better. The notation is when we write a function, vertical line, put an a at the bottom, b at the top. This means first plug b in, then plug a in, and then subtract those two numbers. Okay, so let's go ahead and plug 9 into this, and 1 in, and then subtract. All right, so plugging in 9, we get 9 cubed over 3 plus 9. Minus, when we plug in 1, gotta make sure I put a parentheses so I don't forget to distribute the negative to both of these terms. Plugging in 1, I get 1 cubed over 3 plus 1. Okay, so two of these terms will have 3 as a denominator, so I'll subtract them. 9 cubed is 729, and then I'll get this minus 1 cubed is 1. And then I also have the 9 minus 1, which is 8. Okay, so 729 minus 1, that is 728 over 3. And then plus 8, getting a common denominator, this becomes, so multiply this by 3 over 3 to get 24 over 3. And now adding these, 728 plus 24 is 752 over 3. And that's the same answer that we got using Riemann sums, but so much faster. So one of the takeaways is that Ftc2 is much more efficient than Riemann sums. So why do we learn about Riemann sums? Why not just jump straight to Ftc Part 2 and just do antiderivatives to get areas? Well, if we were to do that, it wouldn't explain, like, well, where does the Ftc Part 2 come from? Like, why does getting an antiderivative tell us an area? So where that actually came from, how we were actually able to prove this result, was we needed Riemann sums. That's where the Fundamental Theorem of Calculus came from. It came from using Riemann sums and showing a connection between them and and antiderivatives. So one important thing I want to note about these definite integrals and when we do them using antiderivatives is we don't need the plus c with definite integrals. Definite integrals are the integrals that have these bounds on them, like the 1 and the 9, because they represent an area under a graph. Since they would cancel if we did write them. So for example, e.g., if I were to have put a plus c in my antiderivative up here and plugged in 9 and 1, we would have gotten 9 cubed over 3 plus 9 plus a c, and then minus, when you plugged in 1, we would have gotten 1 cubed over 3 plus 1 plus that c. But when we subtract these, this minus would distribute to that c over there, and then this c would cancel with this minus c. So we'd end up with the same thing. So for a definite integral, we don't need to write that plus c. For an indefinite integral, we need to write it, because an indefinite integral means general antiderivative. All right, so let's look at another example. Okay, so for this next example, I want to have you all try this. Pause the video for 2 minutes to try this one on your own. 4, 3, 2, 1, pause the video. Pause it for 2 minutes to try example 3 here. All right, so hopefully you've done that. Hopefully pause it for about 2 minutes to try this. And hopefully it wasn't too bad. This one should be another quicker example. So the antiderivative of 2 over x is 2 times ln absolute value of x. It's a definite integral, so I don't need to put a plus c, because even if I did, it would just cancel out when I plug in the -1, the negative e, and I subtract. Now I use my notation. I put this vertical bar. I write negative e at the bottom, -1 at the top, to indicate I'm going to now plug those in. So first we plug in -1 into this, and that gives us 2 ln absolute value of -1. Then I plug in negative e to get 2 ln absolute value of negative e. And then we subtract these values. Okay, so simplifying, we get 2 ln absolute value of -1 is just 1, minus 2 ln absolute value of negative e is just e. Okay, so now this is just some algebra review. What's ln of 1? So ln of 1 is just 0. So it's 2 times 0. And ln of e is 1. So we get 2 times 1. So overall, we have 0 minus 2, which is -2. So we ended up with this negative answer. Why does that make sense conceptually here? Well, if we were to look at the graph of y equals 2 over x. So if I draw some axes. So the graph of 2 over x is really similar to the graph of 1 over x, except the 2 on the top will just double all the y values. So it's a very similar shape. Just all the y values got doubled, so the graph sort of gets stretched a little bit. But the graph overall has the same shape as 1 over x, just stretched a bit vertically. So if I look at the section we care about here, so let's say that's -1, and negative e would be somewhere here, because negative e is about approximately -2.7. So we are looking at the area between negative e and -1. And because that part of the graph is below the x-axis, it makes sense that the area should be negative. So it's good, actually, that we got this negative value as our answer. Let's do another example. Okay, example 4. True or false? The integral from negative e to 1 of 2 over x dx is equal to -2. It's a really similar one. This time, pause the video for about 1 minute to try this. It seems like we should be able to do something very similar to get the answer, at least at first glance. But maybe is there an issue that would make this not work out for some reason? So pause it. 4, 3, 2, 1. Pause that video. Pause it for 1 minute to try this and really think about this. It's especially important on these true-false questions to spend time thinking about them. Okay, so the key difference for this question is this number at the top has changed from -1 to +1. And if we were to go about the same process and plug 1 in to this absolute value, we'd end up getting the same thing, because the absolute value of 1 would be 1, and overall that would give us the same thing. But notice that in the picture, 1 is over here. And if I did the integral, if I looked at the area from -e to 1, that includes the place where the graph is discontinuous. And that is a problem. That is a problem for FTC Part 2, because one of the requirements for FTC Part 2 was we need our function f to be continuous on our interval. And here our function was not continuous. Ooh, shifted over too much. Okay, there we go. So as a result, this statement is going to be false, because FTC Part 2, which is what we'd need to be able to say that this answer is -2, doesn't apply here, since our function f of x equals 2 over x is not continuous on the interval here from -e to 1. Specifically, it is discontinuous. Our function is discontinuous at x equals 0. So because of that, we can't use FTC Part 2 to get that this would be -2. Okay, so I want to make one note about this. So for our purposes right now, we don't know how to evaluate an integral like this, because our function is discontinuous somewhere in the middle, so we can't use FTC Part 2. So integrals like this, so this type of integral is called, it's an example of, it's called an improper integral. And we will look at these in section 7.5. So we'll revisit integrals like these in section 7.5 and discuss methods for computing them. In terms of our goals for this section, we have done our fourth goal. We did some examples using FTC Part 2. And we saw how much more efficient it was to find the area under a graph using antiderivatives, aka FTC Part 2, than using Riemann sums, for example. In the next video, we'll show how FTC Part 2 works with U substitution.